Today we are going to look at a problem that includes both physics and mathematics, specifically how to solve a physics problem to find the work done by a variable force by doing the Riemann sum. Specifically, the problem we will look at is the following. A conical water tank of height 8 meters and diameter 6 meters at the base must have all of its fluid content pumped to the top of the cone. If it is full to a depth of 4 meters, how much work will this require? So this is the problem that we will be doing. And as I said, we will solve this problem by doing directly the Riemann sum. So let us first draw the situation that we have here. So we are having a conical water tank. So we're drawing the water tank. So this is the water tank in the shape of a cone. And we are given the height L of the cone. And we are given the radius of the base, uppercase R. And then we are told that the depth of the water is here, and let me call this a height B, and I will put, without loss of generalization, the bottom at a height of 0. And the water is filled all the way to the height of B, and then we are lifting the water all the way to the top of the cone. So let's say that we have here some element of water all at the same height. And let me call this the height xi for the ith such element. Of course, we have many such elements, and let's say that this element has depth of delta x and some radius r. Let me call it lowercase r. And what we want to do is to calculate first how much work is needed in order to take this element at height xi all the way to the top of the cone. And then, of course, we will want to sum over all such elements by doing the Riemann sum. So first, let me write what is the volume of this ith element. So, of course, the volume is the surface area of a disk multiplied by its thickness delta x. So this volume element is pi times r squared delta x. So I need, of course, to find what lowercase r is. So let me draw here a cross section of half of my cone. The height, of course, is L. And the shorter right side is uppercase R. And then I have my disk with radius R right here. And it is, let's say, a distance of h from the top. So now I have, of course, two similar right triangles here, and therefore R over L equals lowercase r over h, and then, of course, I can express lowercase r in terms of the other variables as I will express lowercase r as h times r over L. Now, h itself is, of course, the total height L minus the position xi of the element. So this is my xi. And therefore I can express r as L minus xi times r over L. I can now substitute that in the expression for the volume element. So we have pi r squared over L squared times L minus xi times delta x. Now that we have the volume element, I can find the mass element. So the mass of this disk is just the density of the water times the volume of the disk. And therefore, the differential amount of work needed to be done in order to raise this element of water all the way to the top is going to be delta m I times g, the acceleration of free fall, times h. But h we already know is just L minus x, so therefore we have here delta mi times g times L minus xi. I forgot this square here. All right, so now we can combine everything together. So we have delta wi is pi r squared over L squared times rho times g times L minus xi cubed. 2 powers of L minus I come from the volume element, another power of L minus xi come from the height to which we need to raise this element, times delta x. So this is the element of work that we need to do, and in order to find the total work done, we need to sum over all such elements. So let's say that we have n such elements. So we need to sum over all of them. So I'm copying the expression for each such element. And then I need to sum over all of them. But we don't want to just approximate how much work needed to be done. We want to find an exact value. So we're going to take the element dx to be differentially small, and then at the same time take the number of elements n to be infinitely large. So we need to take the limit of this sum as n approaches infinity. And we also need to write what delta x is. So delta x is 1 part in n of the total depth of the original fluid. So that's the thickness of each element. So it will be b over n. So I'm going to replace here the thickness delta x by b over n in order to set up the Riemann sum. So this is what we need to sum. The only other thing I need to do is to express what xi is. So what is the height of the ith element? So if I'm starting with, initially I'm at height 0, but then at each increment I, I'm adding a height of delta x. And therefore my xi is just I times b over n. So I'm going to use that in my expression for the Riemann sum. So here instead of xi, I'm going to write I b over n. All right, so now we have here an expression written in a way that is convenient in order to calculating the Riemann sum. So we just need to actually calculate it. Let me just rewrite it a little bit. I'm going to pull out terms that don't depend on I outside of the sum. And if they don't depend on n, I can also pull them outside of the limit. So I can take my pi, rho g, r squared over l squared. Those are just geometrical or physical constants that don't depend on either which element we are looking at or don't depend on the total number of disks n that we have. And now we have the limit as n approaches infinity over the sum of I going from 1 all the way to infinity of what we have left. Now I did leave inside the sum the factor b over n, even though it doesn't depend on I, and the reason for that will become obvious later. So this is what we are going to evaluate. Now, to do this, I'm going to do the following. Notice that I have here L minus IB over N cubed. I'm going to use the binomial theorem in order to expand it. So I have here L minus IB over N cubed. I'm going to use the binomial theorem. So this is L cubed minus 3 times b over n L squared times I plus 3 times b squared over n squared times L times I squared minus b cubed over n cubed I cubed. And then I need to sum over all i's that we have here. So we have 4 different kinds of terms here. A term that doesn't depend on I itself, a term that is linear in I, a term quadratic in I, and a term cubic in I. So what I will need to know is what is the sum as I goes from 1 to n of 1. The sum as I goes from 1 to n of I. The sum as I goes from 1 to n of I squared. And the sum as I goes from I to n of I cubed. So if I just have 1 plus 1 plus 1 plus 1, such going on n times, then of course it equals just n itself. If I want to sum over I from 1 to n, the answer is 1/2 of n times n plus 1. You may recall the amusing anecdote of Gauss doing that in grade school, amazing his teacher. So this is easily demonstrable. Summing over I squared is 1/6 n times n plus 1 times 2n plus 1. And summing over I cubed is 1/4 n squared times n plus 1 squared. If you don't know these expressions, well, of course, the first two are almost trivial. The last two can be easily done using mathematical induction. All right, so now that we have those, we can use them in order to find the sum over all I elements. So we have the sum, as I goes from 1 to n, over L minus I b over n cubed. So this I can write by the binomial expansion. The sum as I goes from 1 to n over L cubed minus, let me pull the L cubed outside of the summation symbol as it does not depend on I. So we have L cubed times the sum over 1 minus 3 times b over n L squared times the sum over I plus 3 times b squared over n squared times L times the sum over I squared minus b cubed over n cubed times the sum over I cubed. All right, so now that we have those, we can evaluate what we have by using the expression that we have here. So this sum equals L cubed times n, because the sum over 1 is just n, minus 3 times b over n L squared times 1/2 n plus 1 plus 3 times b squared over n squared times L times 1/6 n plus 1 times 2n plus 1 minus b cubed over n cubed times 1/4 n squared n plus 1 squared. This looks like a mess, but it's actually not that bad. First thing that we need to remember is that when we sum, we also have the factor of b over n. So let me reintroduce it. So I have a b over n here. So each term will have another factor of b over n to it. doesn't matter whether I write it inside or outside the summation symbol, as it doesn't depend on I, so just put it wherever there was room. And of course, there is a b over n also for each term here. So I'm just writing it wherever I have room to do so. All right. And now, notice that we need to take the limit as n goes to infinity. So since we have different powers of n in each of the terms that we are summing, each of the 4 terms that we are summing, only the highest power of n will contribute. The other ones will be, of course, negligible compared with the highest power of n. So let's examine what's the highest power of n in each of the terms that we have. In the first term, we have the n and n canceling out, so there's only a single term here, which is b times l cubed. So in the limit, as n tends to infinity, the first term will approach bl cubed. In the second term, we have here n squared coming from the product of n and n plus 1. And we also need to divide by n squared, so we get a free term, so we get negative minus 3/2 b squared times l squared. In the third term, we have here many terms, but the highest one will come from the n times 2n, which will give us 2n cubed. When we divide by 2n cubed, we will just 2. 2 times 3 is 6, divided by 6 is 1. So we have plus b cubed times l. And in the last term, we have n squared coming from the first term. We have another n squared coming from the second term. Divided by n to the 4th, which gives us just 1. So we get negative 1/4 b to the 4th. So this was taking the limit as n goes to infinity. So in order to make the notation more precise, let me write here that the limit as n tends to infinity over the sum of L minus IB over n cubed times B over n equals this. The sum, of course, is from I going from 1 to n. All right, so now we have a correct expression written here. In order to simplify this expression, let me do a little trick on it. I'm going to add and subtract the same term from this expression. So I'm going to subtract 1/4 L to the 4th. And of course, to maintain equality, I have to also add 1/4 L to the 4th. Why did I do that? Let me now rewrite this expression in the following way. I will write it as 1/4, which I will pull out of brackets. And inside I have L to the 4th, the last term here, I'm now writing first, minus. And now I have L to the 4th Next, I'm going to take the term with L cubed. So I will have minus 4 times L cubed times B. The factor of course, 4 of course is because we pulled 1/4 outside. The negative sign because minus a negative gives us the positive that we have here. Now I'm going to take the term with L squared. So I have here a negative 3/2. I need to multiply that by 4 because of the 1/4 I pull outside. So you get plus 6 times L squared times B squared. The next term I will have negative 4 times L times B cubed plus B to the 4th. Now, if you're looking carefully at the expression written inside the square brackets, you will recognize it as nothing but the binomial expansion of L minus B to the 4th. And therefore, I can write the limit as 1/4 times L to the 4th minus L minus B to the 4th. So now I can take this and go back to our original expression for the work done. So I'm going back here. So what I did so far is I calculated everything written to the right of the limit operation. I calculated the limit over the sum of L minus IB over N cubed times B over N. So what I have here is pi rho G R squared over L squared times what I found the limit to equal. So times 1/4 L to the 4th minus L minus B to the 4th. So let me continue writing here. So let me just write it in a more organized way. So I'll write it as pi over 4 rho G R squared over L squared times L to the 4th minus L minus B to the 4th. So now we can calculate how much it is. So recall that we are talking about water, and therefore the density of water is 1,000 kilograms per cubic meter. The acceleration of free fall G, if I want to approximate it to only one significant figure, I can take it as 10 meters per second squared. To two significant figures, I can write it as 9.8 meters per second squared, of course, on the surface of the Earth. The diameter, the radius at the base is given, it's half the diameter that is given to us, that was 6 meters, so the radius is 3 meters. The height L of the cone is given as 8 meters. And the initial height of the water level was 4 meters. So now we can substitute it in the expression for W. The first thing that I'm going to do is to check my units. After all, I'm calculating physical quantity. If I get the units to not work out, then it's a good indication that I made a mistake somewhere on the way. So let's look at the units. So first I have rho that has units of kilograms per cubic meter. Then I multiply by G that has units of meters per second squared. Negative here. Then I have r squared over s squared. Both have dimensions of distance. So of course they cancel each other out. Then I have distance to the fourth, so times meters to the fourth. So what units do we get? So I have here meter to the fifth divided by meter cubed is meter squared. So I have kilogram meter squared per second squared. Now, if you do not recognize these units, let me break them in the following way. Remember that kilogram meter per second squared is a Newton, unit of force, because if you want Newton's second law, F equals ma, mass times acceleration. So kilogram meter per second squared will give you unit of force, which is a Newton. But then we have another factor of meter. But the Newton times meter is what we call a joule, a unit of energy, which is great because we calculated work, which is a form of energy. So whatever the numerical answer we're going to get is going to be, we know that it has units of joules. So now let's calculate how much it is. So our W equals pi over 4 rho times G is 9800 times 3 squared, which is a 9, over 8 squared, which is a 64, times L to the fourth, but L is 8, so it's 8 to the fourth, minus 8 minus 4, which is a 4 to the fourth. So now we will, of course, naturally need the calculator to find out how much that is. I can do quickly. 8 to the fourth minus 4 to the fourth is 3,840. And when I calculate it, I get 4.156 times 10 to the 6. And as we said, the answer is in joules, which we already verified. If I want to, I can write it in a more compact way as 4.156 megajoules. So this is the answer for the work done. Let me just make a comment about how to calculate it the short and easy way rather than this long way. So the long way was the calculation using directly the Riemann sum. Usually when you have a physics problem, such as this one, you don't want to use the Riemann sum because it takes a lot of work. You do it only if you are asked specifically to do so, let's say in the calculus course. Usually, what you would want to do is go back here to the expression for the force and reintroduce the delta x and the xi that we have here. So, just to remind you, before we had x here and delta x. So what you would normally do then is use the Riemann sum in order to write it in a different way, there is another way to write the same expression, completely equivalent. This is just it's a lengthy expression. There is an alternative way to write this. And the alternative way to write this is by using the symbol of the integral. And to do this, we need to replace this delta x by the differential measure of integration dx. And then, of course, we need to integrate from x going all the way from 0 all the way to b. When we have this integral, notice what happens. Everything which is written here at the beginning, which I'm now marking, is a constant that can be pulled out. So we have pi r squared over L squared times rho times g times the integral. So what I'm going to do is I'm going to pull them outside of the integral symbol and put the integral symbol here. So this is integral from x going all the way from 0 to b. And this is a 0, not a 6, excuse the writing. Now, this integral is easy to do. What I would recommend to do is to do a change of variables. Let me change variables to y equals L minus x. Of course, I can alternatively also expand using the binomial theorem, which we have already used, L minus x cubed into all its terms, and then it's a polynomial, and then I can easily integrate the polynomial, but that is hard work. If I do this change of variable, then dy is negative dx. So what I will get here, let me continue, let me free up some space so I have a place to write this. I no longer need this. So I will make me some space to write here. So let's do this integral. X goes from 0 to b of L minus x cubed dx. So I can rewrite this as an integral over y cubed. Now I have negative dy, and of course need to adjust the limits, 0 and b. So when x equals 0, y equals L. So the lower limit needs to be L. And when x equals b, y equals L minus b. Therefore, the upper limit needs to be L minus b. Now notice that L minus b is lower in value than L. I can flip the ordering if I also flip the sign here. So my integral is the same as integral from L minus b to b over y cubed dy. But this is a trivial integral, it's just a monomial, just y cubed here, so we know it's 1/4 times y to the 4th, evaluated between L minus b and b, and therefore it equals 1/4 So it's not a B, it's an L. Let me fix that. So this is integral from L minus B to L. Oh, this is much better. I just miscopied before. So I have 1/4 L to the 4th minus L minus B to the 4th. So this is the integral that we have here, and therefore the total work done W is just pi r squared L squared rho G divided by 4 times L to the 4th minus L minus B to the 4th. But this is exactly what we found earlier. So what we did is we found the exact same answer by doing the integral instead of calculating the Riemann sum. By the way, notice that this expression 1/4 L to the 4th minus L minus B to the 4th is the same expression that we got here, which is the Riemann sum. Unsurprisingly, the Riemann sum must be the same as the corresponding integral. So it's not surprising for us that we did get the same expression. It would be very surprising if we did not. It will be a good indication that we made an error. So let me summarize. What we did here is the following. We divided all the water in the truncated cone into disks of radius r that depend, of course, on the on the height. So it could be called Ri, if you like. And of thickness dx. The thickness dx is just the total height of the volume divided into n such thick disks. We calculated the differential work done by lifting this element all the way to the top. We did that by finding the work, which is the force times the distance that we raise it. After finding this differential work, we found the total work done by summing over all such disks. In order not to get just a rough approximation for the answer, we took the thickness dx, delta x, sorry, to be very, very small, and took very many such disks. And then we wrote the Riemann sum. We wrote the Riemann sum as follows. And then we just did all the required algebra and limits in order to find what the Riemann sum is. Then we took our expression, we checked that the units work. You always have to check that the units work. It's a great way, this dimensional analysis approach, in order to spot possible mistakes done along the way. If the units don't make sense, if you get work in units of seconds squared, obviously you did some mistake on the way. So that's a great way. I always recommend to check the units. Then found the numerical value. Then we said, well, there was an easier way to do this, and this is by doing the integral directly. And we checked that indeed our answers agree with each other. So we had two mathematical ways to calculate the same thing. And this way we were able to use the Riemann sum or integral directly in order to solve a physics problem that has to do with work. And that is the end of our lesson.